So again, we're going to look at the fundamental theorem of calculus. There were two parts, and we looked at one of the parts. I think it was the second part. I think I said it was the second part. I don't know. But one of the parts showed you how to evaluate integrals. And this was saying that capital F was the antiderivative of little f. And we're not going to do like a formal proof, but we're going to use this to kind of, I don't know, use it as a way to remember the other part for the fundamental theorem of calculus. So remember, capital F is the antiderivative of little f. And another way of saying that with math notation is if I take the derivative of capital F, I should get little f, right? If I take the antiderivative of little f, I should get capital F. So that's just what that means. So the second part involves taking derivatives of integrals. So if you define a function to be an integral, so let's take a look at this. So some function capital F, and there's a reason why I use capital F, is an integral from some number a to an x value of, I can't use x again, so I'll put a t in here, dt. If I define capital F to be this function, I plug in an x value, so I get a number there, and then I could evaluate this integral just by using this fact. So if I have something like this, the other part of the fundamental theorem of calculus says if I take the derivative f prime, maybe I'll use the ddx notation. If I take the derivative of this side, ddx, then that's going to equal the derivative, of course, of this side. The derivative of an integral, which is this is really weird. And some people might think like, oh, you have to evaluate the integral, and then take the derivative. Well, there's a shortcut. This is actually the other part. I think it's the first part. But the other part of the fundamental theorem of calculus gives you a shortcut. You don't have to evaluate this not x shouldn't be an x in there. It should be a t. So if you wanted to take the derivative of an integral, there's a way that you can do that. And this actually equals, I'll just tell it to you right now, it equals just when you substitute the x in there, because f is the antiderivative, or capital F is the antiderivative. So this would actually just equal f of x. There is no plus c or anything. This is the other part of the fundamental theorem of calculus. You just take this x and put it in there. That's it. But I'm going to show, it's not like a proof, but I'm going to show you kind of a way to remember it. So let's just think about this. So let's go back and think about this. So I have my function defined by an integral, and I know from the other part of the fundamental theorem of calculus that this is just f, capital F of x minus capital F of a. All right, so if I want to take the derivative, like right here, I'm just going to try and show you like a way to remember this. If I take the derivative of this, ddx, that's the same thing as taking the derivative of this, ddx, and that's the same thing as taking the derivative of this. Well, on the very, very right side, I already know, since capital F is the antiderivative, I already know that the derivative, it says it right here, the derivative of capital F gives me f of x. So if I take the derivative here, I just get lowercase f of x, which is what we want. And then you're thinking like, well, what happens to this? Well, this is just the antiderivative evaluated already. So this is just a number. So when I take the derivative of this, this will go to 0 because the derivative of a constant is 0. So there it is. That's it. If you have the derivative of an integral that's set up like this, you can just replace the t with an x. That's it. That's the second part. So we have, I think this is the first part, and these are the fundamental theorem of calculus combined. It's part 1 and 2 in some order. I don't remember which order they are. I'm pretty sure this is part 1 and this is part 2, but there we have it. So like if I have something crazy, so those are the two things that you need to memorize. But if I had something crazy like here's a question. If I had something crazy like this, and they're saying, what's the derivative of the integral of this stuff from -2 to x? And you're like, I don't have an antiderivative formula for that. But this part of the fundamental theorem of calculus says we don't need that. This actually just equals, well, the same function is just I replace the t's with x's. So negative cotangent to the 1/2 of x divided by the natural log of x. That's all you have to do. That's it. That's it. It's like a shortcut. If you're taking the derivative of integrals, it's a shortcut. Something else that I want to mention is what if I don't have an x value? What if I have a function of x? So let's see this. Now this is a tiny bit different. This is no longer just simply an x, it's a function of x. Well, let's see. If I were to evaluate this integral, I mean, I don't even know what the function is. I just know that I would have the antiderivative. So if I were to evaluate this using the other part of the fundamental theorem of calculus, if I were to evaluate that using this, what would happen? So I would get the derivative, right, dx, and I'm going to use that other part of the fundamental theorem of calculus that says you get the antiderivative of f, you plug in sine of x, and then you subtract the antiderivative of f with the pi in there. I'm doing the same exact thing I'm doing the same thing that I did here, where I'm taking the derivative. Well, I know, because that's equal, right? I just evaluated that using the other part of the fundamental theorem of calculus. If I evaluate that, I have to use chain rule right here, right? So that would be f prime, the derivative with the inside the same, and then times the derivative of the inside. So that would be times cosine of x. And then this also would go to 0 because it's the derivative. So this right here equals, well, what is f prime? F prime is just, or capital F prime is just little f. So this would be little f of sine x times the derivative of the inside times cosine of x. So there's another part. So that would be the answer there. I mean, hopefully that makes sense. If not, I'm going really, really quick, but I'll do more examples in class. So if you have a function of x, maybe I'll write that down right next to this. I mean, it's kind of like a corollary. The derivative of the integral, maybe I should put g of x in there. G of x. So if I have some function of x up here, and I'm taking the derivative of this integral, and I have f of t in here, dt, then yes, I just substitute that in, but I also have to multiply by g prime. So this would be f of g of x, and also times g prime of x. So there you go. That's like an additional thing. We'll definitely do a lot of examples, or we have done a lot of examples in class. All right, goodbye.